Hello, my name is Pradika Yadav, and this is the first video on our AI course. So I'll be honest, I'm not really that great at presenting in YouTube, but I really wanted to make something really useful for people who are really curious about AI and really want to understand how it works. And I'm not really following a really hard script or plan here, I'm just kind of rolling with it. I'm going to try to explain things on the way and the way that I wish they were explained to me. So I hope you really find this course useful, and let's get started. AI is growing rapidly to the point where today it has so many topics ranging from speech recognition to computer vision to generative AI. Now, that can make it seem very tough to know where to start. You can be like me and just jump right into a topic. And if you were to do that, I would start off with computer vision because it actually shows you what the computer is thinking and what steps it takes, while in other topics, you don't really get to see what the computer thinks and what steps it's taking. So it can be pretty useful to start off with computer vision. It'll make it very easier to start connecting the dots. But in this course, I will start off with teaching the core concept of AI, what differentiates AI with normal algorithms. So this is it. This is what I think differentiates an AI with a normal algorithm. I know it doesn't really seem that complex. I mean, this is the common core concept. Even if the AI is supposed to what? Do an essay for you, or recognize your face, or go through a maze. This is a common core concept, the loop that an AI has to go through in order to get your output that you want. Let me try to go through each step and explain how it works. So the first step is the input. This is where everything begins. So the input can be anything from an image, a sentence, or a button press. It is the data that you give the computer to start learning from. So here's the difference between a normal algorithm and an AI. A normal algorithm expects everything to be neat and structured, and the input that it expects. But an AI is trying to learn from the input, and it's supposed to interpret. It's supposed to adapt to new inputs every single time. They're designed to take in messy, noisy, incomplete data and try to make sense out of it, try to make patterns from it. We have our input, we have to pre-process the input before we create the model. Because imagine this, you have an image. The computer cannot exactly understand what the image is because, see, an image to it is a whole bunch of numbers. It will not understand it, and it needs the image in a format where it can recognize that it is an image where it can perform more actions upon. And sometimes the data is just way too chaotic, too unstructured to understand. So before the system can actually learn or make decisions, we need to prepare that data. That's what pre-processing is. It's the part where we clean, simplify, and kind of reshape the input so it becomes understandable and usable for the computer. To the fun part, the model. This is what makes an AI an AI. See, this, unlike algorithms, is not exactly a script of instructions. It's more of a pattern detector. It doesn't exactly say, if this is true, then this is the output. It says, based on everything that I've seen before, this kind of input kind of usually leads to this kind of output. And right now, the system isn't just following its rules, it is making the rules. Okay, after the model is done thinking, it gives you something back, an output. And unlike a normal algorithm that gives a single exact value or something, this AI usually gives a guess or a probability that it is this output. For example, if a AI is trying to determine whether it is a cat or not, the AI might return, I am, 90% confident that this is a cat. The next step is critique. The computer basically asks itself, how did I do? It compares its answer and how confident it was with that answer with the real life answer. So it basically compares its guess to reality. And this step is essential. This is where the computer figures out not just what it got wrong, but how and why it got wrong. It's kind of like getting test results back, learning what it did wrong. Finally, it adjusts. It updates based off of the feedback it got from the critique. And this is the most important part of the loop because this is really how the computer tweaks how it thinks, how it tries to get a better outcome. Remember that this is a loop, so after it updates, it will go back to a model and change the model, and then it will get its output again and critique it again, and then it does this on and on and on until it gets a significant or appropriate result. Those of you that have taken engineering, doesn't this look a bit familiar to you? Yeah, it just, for some reason, really reminds me of the engineering design process. This is really random, but I thought that there is some kind of connection between them. Now, let me elaborate a little bit more on the input because I didn't really give that great of a definition in the previous slides. So let's look at what an input could be. So this is just one example of an input. Let's say we're inputting an image. The computer does not see the image like we do. It just sees an entire group of numbers. See, these numbers or from the image are called the features. What basically the different features of the input, what the computer has to learn from. And the label is the cat. It is what the output is expected to be, or what the computer labels it to be. Think of the labels as classes, and another way to say this is kind of like thinking of the features as the independent variable, as let's say x, and then the label as y, or the dependent variable. Now that we have our input, let's get into preprocessing. Preprocessing is a lot more important than many people think, because imagine you're gonna give a computer a whole bunch of numbers, a whole mess of numbers. How will it find patterns from that? Preprocessing could be something like compressing data values, because look at all of this data. It can sometimes be too much for a computer to handle. So sometimes we have to compress the image and only get the most important values out of it so that the computer doesn't have to be as slow or think as much. And sometimes something else could be resizing the images to the same size to reduce bias. Or it could be converting colors to grayscale if color is important so we can get rid of unnecessary data. Sometimes we have to normalize the brightness or the light so that dark and light photos don't really confuse the AI. It's kind of like tuning the sort of contrast. Details really pop out more clearly. It is the same for all types of inputs. It can be the same for text, such as sometimes it would be good to lowercase everything in order to remove the fluff and make a computer do less work. Sometimes it would be good to remove some unnecessary grammatical devices, such as the is not really that useful to computers in this case. Sometimes the words will also be turned into numbers using something called embeddings or one-hot encodings that we will get into later. So basically the sentence will become a basic vector or a row of numbers, something that the system can learn from. Next step would be trying to find all the patterns or create the model, right? But not all AI learn the same way, so they have their own ways to create their own model or algorithm. See, think of it like this. One person learns from reading or looking through tests, reviewing their tests, another by just exploring, and another by doing or going through trial and error. So we're going to break down these different learning approaches. There are three ways a computer learns. And by learning, I mean when a computer adjusts itself to try to optimize its solution. So basically, the three ways are supervised learning, unsupervised learning, and reinforcement learning. Let's go through each of them one by one. First, supervised learning is basically learning from labeled examples. As I showed you before, a label is sort of the dependent variable or y, and we give the computer the labels to learn from. It's kind of like a student being shown flashcards. You could say, give it a picture and say, this is a cat, and have another picture and say, this is not a cat. And then over time, the system continues to look through those flashcards and tries to connect certain features with certain labels, and then it tries to find the patterns to learn from, to start mapping inputs into specific answers. And this is kind of the most common kind of learning. You can think of supervised learning as if the computer had a teacher, and the teacher gives the computer some tests, and the computer can see the test results and what it got wrong. It's unsupervised learning. The computer does not have labels. It's unsupervised. The computer has to learn by itself. Imagine you're giving a system a big pile of coordinates, but don't really tell what each coordinate is. It doesn't really know if this coordinate is in this group of cluster or this city. It just starts to group similar coordinates that are kind of close together. This kind of learning is more about discovering structure in the data by finding patterns, clusters, or relationships. Think of this type of learning as not having a supervisor in the computer learning by itself. And then the next one is reinforcement learning, where it learns from trial and error. This one is different from the other types of learning. Instead of studying examples, the system actually acts or does some in a game and gets rewarded or penalized based on what happens or what action it takes in what scenario. Over time, the computer will figure out which actions lead to better results in which scenarios. It adjusts its behavior. It's like training a puppy, not by telling it facts, but by encouraging good actions. Back at the photos from the last slide to see which one is which. See right here, this is a supervised learning example because you are trying to classify whether this is an apple or a banana. So the labels can be, there is a label and it can be a apple or a banana. This one over here is trying to group together into clusters, and this one is unsupervised learning because it doesn't really have a label given to it. This one over here is reinforcement learning, where the computer learns from its actions. Most reinforcement learnings are mostly used in gaming or maps and etc. The image here is so helpful when it comes to deciding which machine learning algorithm to choose. Now, it might look complicated at first, but let me say it's just kind of like a flow chart that helps you choose the right kind of learning algorithm based off of your data and your goal. You don't have to remember it or memorize it or anything. This is just a cheat sheet. And you don't really need to get too deep into this because this is mostly for topics in the future, what we will cover in the future. I'm just showing you this because this is an amazing resource and we will definitely use it in the future. Before we start really getting deep into it, maybe just doing a slight read through of it might be helpful for you. Let's get a little bit deeper into supervised learning. Remember, supervised learning is when we give the computer the labels. Metaphorically, we give it examples with the answers being labels. We are showing it pictures and we're telling it this is a cat or this is not a cat. It's like the system is a student and you're showing it flashcards. Each image comes with a label, cat or not a cat. Over the time, the system will start to learn patterns, such as it will recognize if this has pointy ears, then it might be a cat. And it has these type of eyes, possibly a cat. Recognizing specific images, it's learning what features tend to show up in cat images, what patterns show up in cat images, really what a cat is. then later, when you give it a new picture, one that it hasn't seen before, it will take a guess. It will say something like, "This looks a lot like the cats I've seen, so I am 95% confident that this is a cat," and I'll say it's a cat. Then, based off of its confidence in its answer and the real answer, it will change its general rulebook. There are two general types of supervised learning. One is classification and the other is regression. Classification is when the labels tend to be categorical, such as this is a cat, this is a dog, or a rabbit. Regression is when you're trying to predict something that is quantitative, housing prices. So in supervised learning, we give the system the answers or labels. Say, this is a cat, this is not, but what if we don't give the system answers? What if we give the system a bunch of images or data points and we don't tell what anything is? No labels, no guidance, just raw data. That is where unsupervised learning comes in. Instead of trying to match the input with an answer, the system tries to find out patterns on its own. It looks for similarities, differences, clusters. Basically, it tries to make sense of the data without a teacher. And actually, I got to work on a real unsupervised learning project during an internship. And it was really cool. I learned a lot, and I'm so grateful I got to do it. So basically, we had access to tons of location data, showing areas with really poor internet, without labels, no categories, just coordinates on a map. Using clustering, I grouped these into regions and helped identify the best possible locations to install new landline connections, based purely on where these problems were. If you're curious, I have posted my example code and a short write-up about that on my GitHub. Feel free to check it out. So now that we know the basics of unsupervised learning, let's break this down a little bit more. There are two main types of unsupervised learning: clustering and dimensionality reduction. Both of them serve different purposes. They both are mainly about understanding and creating structure in messy piles of data. Clustering is probably the most common type and the easiest to visualize. So let's look at this over here. Imagine you have a bunch of data points and it is all unlabeled. We don't tell the computer what categories there are and which data points fit in which category. The data is unlabeled. See, this is what the computer sees. And then the computer is supposed to find some patterns, such as maybe how close some points are to each other, and then map them out. And for this example, this would be what the computer would output. Each color is its own cluster, used for different things, such as maybe grouping search results, or grouping different types of anomaly detection, or even image segmentation. Now on to dimensionality reduction. So this helps when your data has too many features. So imagine looking at a spreadsheet with so many columns, like thousands of columns, many axes, flattening down the data into 2D or even simpler versions, where the patterns become more visible. It's used for multiple things, such as data visualization, like turning high-dimensional data into something plottable. It can be used for speeding up algorithms by reducing noise in the data, or compressing information in smart ways that still keeps the important stuff. While clustering is about finding groups, dimensionality reduction is about finding clarity in complex data. On to reinforcement learning. Reinforcement learning is all about learning from experience, through trial and error. So let's start with an example: chess. Imagine you're teaching someone how to play chess, and you don't just give them instructions. Maybe you'll give them a rule book, but that's it. You'll just tell them to go ahead and play. They will win and lose some games, but after each game, they will reflect back onto what they did. They will reflect on their mistakes, how to avoid that mistake in the future, and perhaps create their own strategies. Learn from trial and error. That's reinforcement learning. Think of it as if an AI was playing a game. So anything that the AI can control is called an agent. For this example, the agent is the AI chess player, the one making the moves, the one trying to win. The environment would be the chessboard, the state would be the current scenario the player is in. Every move it makes is an action, and time it kills the opponent's piece, or if it wins, it will receive a reward or a penalty. And the policy is the strategy that the AI builds over time. The episode would be the full game. Basically, in reinforcement learning, the system learns by trying things out. It will get rewards or penalties based on the action that it takes. And over time, it will figure out which actions are best in which scenarios. Takeaway is that reinforcement learning is all about learning through experience, and it would be really useful for anything that involves making decisions over time, such as games and real world tasks like driving, flying, or even teaching robots to walk. Everything that we have talked about so far, the supervised learning, unsupervised learning, and reinforcement learning, that just falls under one topic: machine learning. It's simply the idea that systems can learn patterns and improve from experience and data, and that we don't really need to hard code every single detail or rule. Now, you might be wondering, wait, is this how ChatGPT works? Is this what's powering things like self-driving cars or art generators? Kind of, but not exactly. See, those big, powerful systems that you have heard about, like ChatGPT or the Google AI, those are not using basic machine learning. They are using a branch of it called deep learning. Learning is called deep learning because it uses many layers of logic stacked on top of each other. I know it's tempting to want to dive straight into building something like ChatGPT right now, but unfortunately, we're not really quite there yet. Deep learning is incredibly powerful, but it's also kind of complex. See, it sits deep inside the world of machine learning, and to really understand it and to use it, we need to build a strong foundation. And the other things that we will do is building that foundation. And trust me, once you got this part down, deep learning won't be as complex. It'll just feel like the natural next step. So who knows, maybe at the end of this course, we might build ChatGPT. This is a quick hint to what a deep neural network would look like. See, they're made up of layers of little units called neurons. This is a little neuron. Each neuron takes in some information, does a tiny bit of math, and passes its result to the next layer. The more layers you stack, the more deeper the network becomes. This is why we call it deep learning. Each deep neural network has its input layers, its multiple hidden layers, and its output layer. Give it an input like a photo, a sentence, or a sound. That input passes through multiple layers, each one pulling out patterns, details, or meanings. One layer might notice the lines or edges, the next might combine those into shapes, and the next one might find out if it's a cat or a dog. And at the end, you get an output, a prediction, or a decision, or even a full paragraph of text. Let me just get this out of the way right now. You don't need to be a math expert to follow this course. Like, seriously. If you know some basic algebra, like how to solve for x, or understand some simple graphs, you're already in good shape. See, throughout the videos, I'll try to explain the math in a way that is simple and understandable. And if you ever see a scary looking formula, don't panic. I'll walk you through what it means, not just how to calculate it. In fact, if you're not really into math, you can even skip those parts and just learn the core ideas just fine. No, the formulas can look scary at first, weird symbols, Greek letters, some weird signs, but I promise you, once you learn what each part means, it's actually kind of satisfying. So, personally, I loved seeing how math and computer science aligned. Like, math do something useful and actually kind of cool, like generating images or understanding language. It's honestly one of the most satisfying things ever. That said, if you're curious and want to understand what's happening in the math area, here are some math areas that show up the most in AI and deep learning. Statistics and probability. Some things like confidence intervals or normalization appear a lot throughout this course. And linear algebra, vectors and matrices, dot products, matrix multiplication. See, these are really helpful when it comes to processing data or using preprocessed data. Data gets transformed through matrix operations. Multivariable calculus is pretty helpful as you will see a lot about gradients and optimization and chain rule and derivatives used a lot when we actually get into training the models. Sorry, I just wanted to add some more things onto statistics. So it would be really good to know some probability notation and interpretation. Like, you'll often see things like the probability of A given B, or P hat or Y hat, meaning an estimate or prediction of a probability. Or sometimes you'll see E brackets X, meaning the expected value of X. See, once you know what these symbols mean, formulas will become much less intimidating. Thank you so much for watching this intro. Seriously, like, I know this is a lot of ground, and if you're still here, that means that you're actually curious and invested, and thank you for watching. Now, this is just like the foundation, or just a intro. In the upcoming videos, I plan to dive way deeper, especially into supervised learning and the different types of machine learning in more detail. So I plan to break it up like this, like one video explaining the core concept or math behind each algorithm, and another full walkthrough on how to code it from scratch or use it in practice for each supervised learning, unsupervised learning, and reinforcement learning. And I was also thinking about doing an entire video on just pre-processing, because let's be honest, this step deserves way more attention than it actually gets. And to be fair, everything is not fully mapped out yet. I'm just figuring it out as I go. But trust me, I am planning to go really deep. I want this to be the kind of resource I wish I had when I started. So if you're into this, stick around, ask questions, replay what you need, and let's keep going. Because the deeper we go, the cooler this stuff gets, to be honest. Goodbye.